Hey guys, we're going to talk about Newton's third law today. It's our wrap-up of Newton's laws. And, well, you've heard of it. You've probably heard that for every action, there is an equal and opposite reaction force. For every action force, there's an equal and opposite reaction force. Well, we kind of upgraded this if you look in here, and we're saying that for every action force, there's an equal in magnitude, so an equal in size and opposite in direction reaction force. And I'm going to add one extra line in here myself. All right, because this is important to realize, is that it's on a second object. Now, when I talked to you guys about first and second laws, I was very careful to make clear that those are about all the forces that are acting on a single object. Newton's third law is a little bit different. It's about an interaction, all right, between two objects that involves two forces, two objects and two forces. And we call this interaction, all right, it's labeled an action-reaction force pair. Sometimes it's called action-reaction pairs. So let's say that you and a friend are messing around and you're standing on a skateboard and you are being silly and you're playing a game where you want to see who can push who off the skateboard. Don't try this at home. Okay? And we'll call you Jim and Bob. Okay? So between you guys, we're not talking about any of the other forces that are acting. We're just talking about the force that is between you guys. This one right here. All right? Your push force, all right, is the force of Jim on Bob is equal in magnitude and opposite in direction of the reaction force of Bob on Jim. And that's how you'd go ahead and you'd write it out if you're writing out mathematically. These two, same thing. Okay? So notice that we have two objects, and we kind of say them backwards. The force of Jim on Bob is equal and opposite to the force of Bob on Jim. Let's look at a few other examples here. All right, make this bigger. So take the scenario where you hit a baseball with a bat, and what you are given is that the bat, hit something. So the bat hits the ball, okay? Object 1, object 2, and there's our interaction, right? Okay, so the bat hits the ball, object 1 and object 2. And so what is the reaction to this? The ball hits the bat, 2 on 1, and here's our interaction. Okay, I'm going to abbreviate that. It's a long word to fit in there. So let's keep going. You ever kind of think about how you actually move? Well, a sprinter starts running, and so we have the sprinter, and we have pushes on the ground. Okay, there's our interaction. This is our interaction. Our reaction force is the ground pushes on the sprinter. 2 interacts with 1. You also have a fish swims. A fish, object 1, pushes the water backward. There's our interaction. Our force. And we have the reverse. The water, object 2, interacts, pushes on object 1. All right, so hopefully you're seeing there's a pattern here. Object 1, object 2, object 2, object 1. If you can identify the two objects, you can pretty much solve anything that's a Newton's third law problem. Because you know if you've got those two, then it will be just flip them for the answer. But let's go ahead because this makes sense. I can buy it. Newton's third law, equal and opposite. I got it. Let's talk about one other story. If you watch the video about the best third law video ever from Veritaserum that I linked, you'll talk about this. Okay, so the Earth pulls on the moon. Okay, and the moon pulls on the Earth. Okay, not a problem. We'll do our little circles, right? Our little squares, the Earth and the moon. Here's my interaction, and then do it the other way. The moon pulls on the earth. Now think about what this means. This is saying that the force of the earth on the moon is the same, all right, same size, opposite direction of the force of the moon on the earth. Earth, moon. Okay, what do we have here? We have the force of the earth on the moon. All right, and the force of the moon on the earth. Think about this. Ask yourself, do you really believe this? Okay? All right? Ask yourself, do you really believe this? And I have a feeling there's going to be a part of you that says, why? How can that be? The earth is so much more massive. It's so much bigger than the moon. Shouldn't the earth pull with more force? Hold that thought. We're going to go ahead and we're going to take an even more extreme example. All right? And then we're going to go into the big old whys of it. So let's say you trip and fall off a step. So why do you fall? You fall because the earth pulls on you. And what is the implication of that? Well, the implication is that you pull on the earth. Okay, all right, okay. Let's go through this. Let's write it out because this is the part where we start losing people, between the earth and the moon and the earth and you. All right, earth pulls on you. You pull on the earth. And we're supposed to buy the fact that the force of the earth on you is the same as, in opposite direction, of the force of you on earth. Huh? Why? Why? All right, let me tell you why. The why is because of what's hidden in this equation, all right? You know, we talk a lot about how forces, there's words in academic classroom and the word outside, and they kind of mean different things. Well, force is one of those words. It turns out that all this time that we were talking about force, like say two football players, they hit each other, they were saying, oh man, they hit with all that was a big hit, there was a lot of force. That we're not actually seeing the force. We're not seeing the force. We are seeing the change in motion. We're seeing the acceleration. So the force may be the cause, but what we actually view with our eyes and what we tend to refer to incorrectly as a force is the effect. All right? We see the effect, which is the acceleration, the change in motion, and we misname it. We call it the force, okay? So what's really happening? Let's pull this back and say what is, and I'm borrowing from another video that I saw, what is unseen? Because there's a lot of physics that we don't see, and that's where we get confused, because again, what we see is a little bit different. So let's go back to our idea, okay? And I'm going to do that force is equal to ma. I'm going to rewrite Newton's law here. So the force of 1 on object 2 is equal and opposite to the force of, actually I'm going to use the moon one, I think. Hang on. Okay, and I think this is going to make a bit more sense. I'll even use mine. Use the earth on you and you on the earth, okay? Let me see. Erase. Not the right buttons. Intriguing. Backing myself up just a little bit here. Okay, earth on you on the earth, and we are going to remember that force is equal to mass times acceleration. So let's talk about the force of you on the earth, okay? Or, I'm sorry, the earth on you. Well, compared to the earth, you probably have a really little mass, all right? And compared to you, the Earth has a really big mass. So what's happening here? Well, your little mass has a big acceleration towards the Earth, and the Earth's big mass has an itty bitty, can't even tell it's happening, acceleration. So when we say that the forces are equal, but we have a hard time understanding that, it's because of the fact that what we're not seeing equal forces. We're seeing unequal changes in motion, okay? So forces are equal always, okay? Change in motion, that change in motion depends on the mass. So if we go back up and we look at the moon problem, right? We look at the moon and the Earth. So here's our moon, here's our Earth. So here's our Earth, here's our moon, sorry. Here's our moon, here's our Earth. And we're saying, all right, that if you want to say that the bigger mass pulls with the bigger force, the reason why that's a false statement is because it's only half the statement, okay? So the bigger mass pulls with the bigger force only if the acceleration is the same, okay? All right, the object has a bigger acceleration with the bigger force only if the mass is the same. So you have to kind of watch out for that. So this, right, these two things do not apply. All right, because you can't just say a bigger mass equals a bigger force. You have to include the if. All right, so here's our big idea. Let me put a big circle around the biggest idea here. This is what we need. This is the key to understanding Newton's third law. All right, the forces are equal. The forces between the objects are equal, but the change in motion can vary based on the mass. All right. So that's our big idea right there. Let me give you, so here's where we have, here's another place where there's a big misconception. So let's say that we have those two guys that we had earlier that are standing on their skateboards and they're having their little push war here. See who's going to get knocked off the skateboard. And we say that the force, this was Jim and this was Bob. The force of Jim on Bob, pushing on Bob, is equal to, and opposite to the force of Bob pushing on Jim. And we say, okay, I get Newton's third law. Yay, they're equal and opposite forces. Okay, how do you move? What? How do you know who wins this push war? All right, how do you know? Well, here's the thing. This is how you know. This is Newton's third law. All right, it has two objects. When you're talking about who wins, you are looking at one object. So here is object 1. Here is object 2. You know who wins, okay? Right? Who wins is based on who has the biggest net force. Okay, all right, so is this net force, all right, the net force on Jim bigger than the net force on Bob? Okay, because there's more forces interacting than just the action-reaction pair. So we win tug-of-war contests, not because of Newton's third law, but because of Newton's first and second, okay? Newton's third law just tells about the interaction between two objects. Newton's first and second law tells about how we actually move. All right, and just to go through the other slides so that you have them here very brief. This one is a very common physics problem. Imagine a bug hitting a windshield of a semi. What force pair occurs? Well, you've got the bug hits the truck and the truck hits the bug. Which force is bigger? Neither force is bigger. Which object has, and that's this, which force is bigger is neither, because of Newton's third law says they're the same. Okay, so which object has the greater acceleration? Well, the mass of the bug is pretty small and the mass of the bus is pretty big. So if this is going to be true, that the force of the bus on the bug is the same as the force of the bug on the bus, that's going to be same, then the small mass of the bug has to have a big acceleration and the big mass of the bus has to have a small. So which one has the bigger acceleration? The bug, because he's now going the opposite direction. All right, short ones. So common examples, gun. So when firing on a gun, the gas is pushed forward on the bullet and backward on the gun. So let's do our stuff. Let's do our boxes, which is our objects. All right. When firing the gun, the gas is pushed forward on the bullet and backward on the gun. All right. So this is kind of an awkward statement. I think what they're saying here is that you have the bullet. All right. The gases push the bullet and the bullet pushes the gases back. When the gases push back, all right, then you have the gases on the gun. So there's kind of like two sets of force pairs in there. So just kind of watch what they're asking for. If they talk about the gas in the bullet, you know the reaction is the force of the bullet on the gas. If they're talking about the recoil, it is the force of the gas pushing on the gun, all right, pushes the opposite direction. Next one. Ooh, this one's kind of crazy. Okay, so, all right, while breaking bricks, you have to exert enough force on them to break them all. So what are our objects? Bricks. When you hit the bricks, these are our two things. So if you hit the bricks, then the bricks hit you with equal and opposite force. All right. Finally, when a rocket lifts off, the gases are pushed out of the back of the rocket, which means what? So which means that the rocket pushes the gases down. All right, so rocket pushes the gases down and gases push the rocket up. There's our force pair. All right, that covers it, and we'll talk later.